Greetings, programs. This is Astronomy Daily Live, coming at you live at 2 hours UTC. It's almost 2 hours UTC. It's still 1:59, so now it's 2 hours UTC. Hey, everybody. Hope everybody's doing great. Hope you had a great day, great evening yesterday, past 24 hours. I need to make one correction. Right at the end of last of yesterday's show, I mistakenly said that uh, in one day we will have traveled 1,000,000 kilometers. No, 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 no. That's in an hour. That's in an hour. That whole thing was to figure out how far we move, each and every one of us move in a day, and that works out to be, and I still have it in my handy dandy calculator here. Every good scientist has a calculator, an actual physical calculator within arm's reach, practically at all times. Now, sometimes that's not possible. But anyway, I'm just going to add these up again. Plus recall B plus recall C equals, yeah, so 20 million kilometers per day. 20 million kilometers per day. And that's just us sitting on the Earth, rotating once along the Earth's axis, the Earth's motion around the sun for one day, and then the sun, and of course, the rest of the solar system, including us, moving around the center of the galaxy in one day is 20 million kilometers. So yeah, I just wanted to correct that. Don't want to make those numbers too small. We want big numbers here. So yeah, hope everybody's doing good. This is Astronomy Daily Live, and this is for the 1st of March 2018. So we're entering a new calendar month. The month of February did not have a full moon in it. Full moon is coming up very, very soon. I think it's within the next day or so, something like that. And so yeah, and we're also going to have another blue moon at the end of March. So this series of 3 months, January, February, March, um, in terms of sort of unusual um, uh, things, it's pretty special, pretty special. So enjoy it while it lasts, because it won't. It will come back. Don't know how often this happens, but I can guess that it's pretty rare. It's pretty rare. So this live stream is just a casual, fun, hopefully Hey, am I back? I think I'm back. Technical things. The this this laptop is okay. Well, it looks like I'm back. So for some reason I lost power on my laptop and on my Linux screen. Okay, not the computer itself, on the Linux screen. The the uh, the battery in this laptop doesn't work, so it always has to be plugged in. So if power goes out there, this laptop will go off. Um, but that at this exactly the same time that the laptop went off, my screen, my Linux screen, which is on a completely different power source, also went black, cycled power. The Linux machine stayed on. So anyway, I'm back. Miguel Johnson, hey, hope everything's well. You're taking a break from mastering. Cool, 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 cool. Yeah, I need to get back into um, composition here myself. I've got a, I mean, I don't have a studio, right? I mean, I don't, and the problem that I have is that in this house I have a ground loop problem, um, and so uh, I've tried and tried and tried to um, um, get rid of the noise in recordings that I've made, and sometimes I'm lucky, and sometimes I've not. But you know, it's a buzz, it's a hum, and for the most part, I'm able, you know, to filter that out. But that's not the quality that I want to be able to put out there. And as I said, you know, sometimes uh, uh, um, the noise seems to be really, really low, or you know, for some reason, like the frequency band, I'm able to filter out properly, so you know, it's not there. But yeah, I need to get back into composition. It's been quite a while. So, but yeah, I'm glad. Yeah, audio interfaces, get rid of that. Okay, okay. You should get a Focusrite USB audio interface. Okay, I'll look into that. Yeah, because I would like to remove the noise at the input if I can, if I can, because yeah, that just makes for a much more pleasant recording experience. You know, recording and mixing. I just use Audacity to record and mix. I just I just have a keyboard. I mean, I do have a guitar too, but I mean, I basically um, um, compose songs sort of one track at a time. So I can use something like um, um, Audacity, you know, that has, as far as I know, just a single input, and and uh, and that seems to work really really well, you know, to mix um, afterwards, and it actually helps in the um, creative process, you know, because I can lay down a track and then listen to it and be like, oh, okay, I think I want to add this, and then I do that and listen to that, and it's like, okay, it needs this. And but anyway, this is not a music live stream. This is an astronomy live stream. So let's get into astronomy. Hope everybody's doing really really well today. Those that are watching live, those that are watching this later in the future, I hope the future is well. The past has been pretty good. Not too bad. Not too bad. I've got the hydrogen hydroxide again tonight, HOH, just because it's so soothing and calming. Um, so yeah, cheers. Now, Miguel, this is a fun, casual gathering of friends, and you know, the main focus is astronomical things, but uh, one of the things that is definitely pertinent is astro art, and that includes things like space music and all of that. So music is very, very much relevant to this. And in fact, I've been working for a number of years um, 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 along with some others who have been looking at taking data and converting it to sound, and actually instead of just having that be sort of a cute thing, that's kind of fun um, um, to listen to. I want to take it to the next level and actually use sound to do the analysis um, of this data. Just like, you know, we'd create a picture or create a plot or anything else. There's a lot of information in sound that, maybe we can't necessarily see all that well, but we can hear really, really well. The dynamic range of our ears is astonishing, right? It's absolutely astonishing. Um, oh, I forget the numbers now, but it's absolutely huge, right? In terms of uh, how faint and how loud we can hear, and the frequency range isn't too bad either. It's not too bad. So our ears, I dare say, are maybe the most sensitive organ we have. Um, but and I think that yeah, um, we don't. Uh, well, I think we take hearing for granted and sounds for granted, and um, um, as a musician, uh, I um, I definitely greatly appreciate sounds of all kinds, and I think to be able to use sound in science, to do the analysis of data, I think that would be a very, very cool thing. Hey there, Susan Hunter. Nice to have you in the chat in Florida. Cool, cool. Yeah, saw you on Deep Astronomy um, earlier today. Sent you an invite, and here you are. So glad you finally found me. Um, yeah, uh, it's kind of rough to get noticed, but so I'm counting on you folks, to spread the word. Um, I'm doing as much as I can, but I I I don't want to become sort of a nuisance, and I don't want to be rude, and so I sort of hang back and sort of hope that folks find me, and you did. So good for you. Good for you. Um, yeah. So just just got done watching the Weekly Space Hangout. Um, always a good show. Shout out to those guys and gals over there. Awesome show. If you don't um, know about um, the Weekly Space Hangout, check them out on YouTube. They do a show, yeah, every Wednesday. Um, is it every? No, it's been changing around recently, so it's really hard to know. Uh, exactly when they're going to be on next. I unfortunately don't pay attention to any of those kinds of things. I just, I've got the notification sent. So when I um, get the email, it's just like, oh man, I've got to jump over there. Um, so I did. They always have a great show, great information, great news, awesome. Check them out. Smart smart people over there. If you want to learn a lot of things, yeah, for sure. But that is just a weekly show. Um, Mine is a daily show, so the vibe is different, and I don't feel the pressure to pack a lot of things in and try to cover a lot of information because I'm going to be here tomorrow, probably. So yeah. Hey there, Uncle Bill. Are you doing the ninja thing tonight? Watching 50 or 60 shows at the same time? I hope so. You got to keep the level up, right? You can't be slacking, right? So hope everybody's doing great. This is also a show about science and the scientific process. And for me, that starts with being curious about things, and being curious about things, at least to me, means sort of two things. It means being um, skeptical, but also being um, open-minded. So when you get new pieces of information, look at those things really hard. Take a nice hard look at all these things, and you know um, question. Just make sure to question, and but at the same time, be open to possibilities and to different perspectives on things. Don't close your mind off just because it sounds silly or sounds strange. Um, pretty, I would dare say that um, uh, that that's sort of how science goes, right? Now, Miguel distracted me again. I was reading his thing. I heard how you were talking about. Okay, yeah, yeah. I wonder how this affects us um, um, in relation to objects that are not moving at all. Wonder how this affects us in relation to objects that are not moving at all around the galaxy. Talking about how we're moving through space-time through a galaxy at high velocity. I wonder how this affects us in relation. Hmm, not quite understanding your question, Miguel. You're going to have to rephrase. This is pretty dense matter up here, so it usually takes me a little while to figure things out. I eventually do, or at least make some kind of a good guess. So ask ask that again. Ask that again. See if you can clarify and you know sort of get rid of some of the density in this head. Yeah. All right. Well, cheers. What I thought that I would do tonight is actually go through a paper that one of my subscribers sent to me on some structures that they have found in the center of the Milky Way galaxy. I sort of thought maybe that I would just go through that paper. What I like to do, and is when I get a piece of news of some sort, one of the first things that I do is I go to the published scientific paper, and I try to decipher it, and that's just the skeptic in me, okay? Because uh, when I read a news item from um, um, the media, it's usually either incomplete or wrong. um, because the media, I mean, it's hard to interpret these papers. It's really really hard. They are technical things, and you sort of have to know. Uh, you have to be able to understand um, what they're talking about, and sometimes that's really really hard. It's really really hard. So, but what I like to do, and what I prefer to do, even if it's going way over my head, which they usually do, is I like to, you know, get the information from the horse's mouth, right? So I like to get it from the person who is doing the research, writing the paper, getting it published. And getting it on archive.org. Archive.org, if you haven't heard about archive.org, it is a great resource. It is the bleeding edge uh, to hear about everything in terms of research. And it just doesn't have to be the astronomical type, it can be all kinds. So it's arxiv.org. So that X is like a chi. It's a Greek letter chi. So archive.org. So if we go to archive.org, they update their lists every single weekday, starting at 0 hours UTC. So we're currently at 224 UTC, which means that the latest and greatest papers have now come out. And so what I'm going to do is I'm going to shoot over there, and you can see new submissions for Thursday, the 1st of March, 2018. So depending on where you are on the planet, maybe it's the 1st of March, maybe it's still the 28th of February. Yeah, don't know. But archive.org is very, very awesome if you're into any kind of science, physics, mathematics, computer science, biology, finance, stats, electrical engineering, economics. These are all the latest papers that have come out on these subjects, and uh, these are papers that have been um, um, approved for publication, but they haven't been published in the journals yet. But they have been published in terms of the internet. So you can go here and find the latest astronomical papers that have just come out like hours ago, right? Hours ago. And this is a way to see what is the bleeding edge of astronomical uh, topics. Isaac Author is awesome. Is awesome. Shout out, shout out to him. Check him out. Isaac Arthur. Isaac Author. Isaac Author or Isaac Arthur. It's probably Author. Uh, uh, Figure out a way not be affected by the gravitational pull. Okay, yeah, yeah. It's an interesting thought, Miguel. I think keep thinking about that because that's interesting. Oh, he uses your music. That is very cool. That is very very cool. Yeah, that's um um Rick Beato last night had a guest, Rhett. Rhett, I don't remember his last name, but he was talking about um, writing music for YouTube channels and all that. And Beato's comment was is that it's hard work that nobody wants to do, but it pays the bills. So he does it. So yeah, cool. Anyway, so archive.org, check those or um, check that out. Uh, what I like to do is I just like to go through them each day. And I look at the titles, and if there's anything interesting in the titles, then I'll read the abstracts, which is sort of a longer description of what's in that paper. Uh, yeah. Lots of math, lots and lots of math. A good way to describe things, but yeah, mathematicians, can sometimes go into fantasy land, and whew, man, get you dizzy. Isaac Arthur. Okay, Isaac Arthur. Yeah, that's sort of what I thought. Uh, anyway, but so one of the members of this channel and also of my Discord channel, which you can see in the description below, he pointed out, and I think his name is BillN.com. BillN.com, is that it? I'm going to go over to my Discord channel over here and find out. Yeah. Oh, BillN.net. BillN.net. Um, anyway, he found a paper that looks pretty interesting. So I wanted to just run through that really, really quick. I think I want to do an object of the day today as well. So let's see if I can find. Let's see if I can find this paper. The title is "The Magnetic Field in the Central Parsec of the Galaxy." Of the Galaxy. Should be able to find it that way. I didn't completely spell it right. That's frustrating. Central. CEN. Central Parsec of the Galaxy. It should pop up here. Why didn't it? I think magnetic field in the central parsec of the galaxy. That should do it. If that doesn't do it, I'm going to quit. There we go. Took my threat seriously there. So this was an article that BillN.net posted up on my Discord channel, on the Astronomy Daily Live Discord channel, and yeah, I just wanted to sort of go through it a little bit, look at it with you, maybe explain a little bit of what they're observing. So they're looking in what I would call the thermal infrared. So they're basically looking at heat, right? 12.5 micron wavelength light is essentially just heat. But in this case, they are looking for polarized light, because polarized light, um, uh, you can sort of infer from that the light um, is going through some kind of an organizing structure of sorts. Now, polarimetry is definitely not my thing, so I'm gonna, over the next couple days, uh, I'll I'll dive into it a little bit more, because I definitely don't want to lose lose my edge in terms of knowing what these guys are talking about, right? But the basic idea is that um, there are these magnetic fields in these clouds of dust and gas, and because this dust and gas uh, is slightly charged in some way, which isn't really talked about much, but slightly charged in some way. Any kind of a magnetic field is going to sort of line those particles up, and so when light goes through this dust that is sort of all lined up in one way, then that light becomes polarized. You only see one polarization, or at least one polarization is stronger than all the others. And so that's more or less what they're observing here. So let's go through it a little bit. This is a really great paper. Most papers are, if you want to get a history of all of this, um, it's a great way of sort of I'm learning a lot of things about the history of the observations and how they came to the conclusions that they've come to. All of that, great stuff. They still say that there's a black hole in the middle. Yeah, we'll see. We'll see. Haven't seen it yet. Seen all the effects of it, or at least our models say that. But the cool thing is that they um, what I sort of found interesting about this paper uh, is the observations that were made and the data um, collected. Uh, Kind of an interesting camera. It's called Canary Cam, and let's see. I wanted to. Yeah, it's looking at the sky uh, quite a bit, quite a bit for sure. Let's see into the pretty pictures. Um, what what was most interesting to me was all the calibrations that they had to do. So they have this instrument, and it's like, okay, how do you know how do you know that it's doing what it should be doing? And so they had to take um, a bunch of data, just to sort of prove to themselves that what they were seeing was what they should have been seeing. So they found in section 4.1 here, um, they found a object that um, they already knew um, uh, was was bright, and at least 4.5% of the light was polarized. Uh, and so they can point their telescope and their instrumentation at that, collect their data, and see if they get the same um, numbers. And it turns out that they did. So that's nice because they know that at least what they're measuring is probably correct. But then they had to do the other side and say, okay, let's look at um, some object that is completely unpolarized, just to confirm that the instrumentation that we have isn't putting in some kind of a polarization signal. And when they did that, they found Not very much. Very, very, very small, like 1/4%. So that's more or less zero. So that works out really, really well too. So far, so good. Cheers. I better pop up my chat over here just in case you all are just taking over. Dun, 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 dun. Your name smells like. Have you ever heard of that guy who is developing warp drive in his uh, garage? Are you talking about the EM drive? If you're talking about the EM drive, I think that's extremely interesting. Extremely interesting. I don't know enough about it. Um, yeah, okay. Well, I'll have to look for it because I know, I mean, if you're talking about the EM drive, oh, it's not the EM drive, warp drive, huh? Okay, I'm gonna have to do a little bit of research about that because, yeah, um, as I said, my attitude is completely open, but I'm also extremely skeptical. So you're gonna have to, you're gonna have to show me. You're definitely gonna have to show me. So one of the other interesting things to think about in terms of, you know, first, they make sure that the instrumentation is actually working. So they look at an object that has, known characteristics, they make the measurement, and they say, okay, we got that one. Okay. Then they look at um, they look at another object that doesn't have any of the characteristics, and they measure that, and nope, there is nothing there. So instrumentation looks like it's working. It's working really, really well. But you got one more problem that you have to deal with, and that is, if you want to be making observations of an object way over there, right, way, way, way over there, uh, and in our case, we're talking about like 30,000 light years away. Well, you have, and if you want to make a measurement of stuff at that location 30,000 light years away, then you have to take into account all the stuff in between you and that object. And so that's what they're doing here. Okay, they're actually looking at all the stuff in between, say, in the center of the galaxy and us, and having to take into account, the polarization. I'm getting into going the wrong way here. So that's a long discussion here about how they did that because it's patchy. There are clouds of gas and dust. What it comes down to, right, is that there are these huge clouds of gas and dust between us and the center of the galaxy, and it's patchy, right? There's thicker spots, thinner spots. Some of them are lined up, some of them aren't. It just it's a big, big, big mess, right? And so in this, section 4.3, which is really, really long, um, they get into the details of how they worked out a way to separate out all this stuff. So it's all they were left at, hopefully, supposedly, at the end. All that was left was just a polarization map of the region that they actually wanted to be looking at. And so that's what this is. I'll zoom out a little bit here. So what this is showing, and I'm actually going to go to a different diagram here in a second, but just so you sort of understand what's going on. So um, the coordinate 0, 0 here would be the center of the galaxy, the physical center of the galaxy. And then each one of these tick marks is 1 arc second off of that. So what? We're talking 10, almost 10, 20. So we're talking about 400 square arc seconds here. So remember that an arc minute is 60 arc seconds. So this is 1/6, 1/3 of an arc minute from here over to here. So it's a very, 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 very small patch of the sky that they are um, um, looking at and making these measurements. So what you're seeing here, and now I'm going to zoom in a little bit just so you can see these lines. Okay, these are the magnetic field lines that they measured, and they show two things at the same time. They show, depending on their length, right? Depending on how long they are, that's showing the strength of the magnetic field. So how strong it is. And then the orientation or the direction of these lines shows the orientation of the magnetic field, right? So it's like a vector, right? It's showing magnitude and direction. So that's sort of how to interpret these. And, they've set up a grid, right? This is actually an evenly spaced grid. If you look at the centers of all these things, they're all evenly spaced. But because of the magnitude and direction of these fields, it changes. It's very dynamic, right? It looks like they're all aligned and really, really tight here. And then here, there's not much at all. So actually, the diagram that I sort of like in all of this is this one, not that one, is this one. Because this sort of really, really shows, at least to me, what's going on, right? So they're saying that the red and brown lines indicate regions of coherent vector orientations on the inner edge of the northern arm and in the regions of these compact objects, they call them, which, stars, protostars, something like that. So here's where the magnetic fields are very, very strong and lined up, right? So yeah, very, very cool. And then let's see, the blue. Did they talk about the blue lines? So the green lines indicate some kind of north-south structures. You see how these are all sort of aligned north and south. North is up, and east is to the right. I think that's right. But you see how all these line up. So drawing these colors on here is a little bit hard. But if you go back to this guy, where you're just looking at the actual data, so you can sort of see that all these are lined up north-south, lined up north-south. I think they said there were a couple of here. Yeah. So, when you read these papers, sometimes you have to flip between stuff because, they like to make lots of pictures. So those are the green ones. Let's see, the blue lines trace coherent structures along the east-west bar. Okay, yeah. See, so uh, there's a north-south structure here, and then there's this east-west structure here, and then they also point out places where polarization seems to be at zero. So those are holes, perhaps there are holes in the clouds or something like that. The interesting thing, and what the news article pointed out, and I haven't been able to dive into this paper deep enough to know if they mentioned it or not. I assume they did. Is that there seems to be connections between these structures. So yeah, what's going on there? Who knows? but it's some really, really great data collection, and trying to figure out, you know, what's sort of in the foreground or between us and it. That's really hard stuff. But it sort of looks like, maybe they worked all that out. So I think that's very, very cool. Very, very cool. So what I want to do is I want to do an object of the day. I'm not doing this every single day, but I like to do it a few times a week or so. And I think I'm going to pull from the Messier catalog again, just because these are, relatively bright objects. Most of them you can see with a pair of binoculars if you know where to look. If you have a telescope, you'll even be able to see them better. You'll be able to see some details. They'll look a little brighter. Yeah, very, very cool. But um, the Messier catalog has 110 um, so-called non-stellar objects. And those are just things that aren't stars. So they could be galaxies, they could be globular clusters, they could be open clusters, they could be planetary nebulae, or they could be gaseous nebulae. And there's 110 of them in the entire sky. So I'm going to use random.org to choose a number between 1 and 110. So drum roll, please. Boing. Oh, M20. M20. Now, oh man. I think M20 is a big globular cluster in Sagittarius. I'm pretty sure. I'm pretty sure. But what I like to do is I like to go to an astronomical database called Simbad. And let's look for M20. So we'll go to the basic search. I'm gonna get a drink of this hydrogen hydroxide here really quick. Cheers. All right, so let's type in M20. Simbad search. Oh, galactic cluster, open cluster. All right. It's right next to the Trifid Nebula. Okay. I'm cheating a little bit. I'm looking at the picture already. So usually what they always show first is just the position of this object in the sky. So these first three numbers are what's called right ascension, and these last three numbers are declination. So it's sort of like a longitude and a latitude in the sky. Now there's a bunch of different coordinate systems that are used. There are four of them that are pretty commonly used. The most common one, though, is um, what's called the equatorial coordinate system, and that's what these are. So 18 hours, 2 minutes, 42 seconds, and then a declination of negative 22 degrees, 58 minutes, 18 seconds. And you can also see that it looks like this open cluster is moving towards us at a velocity of 2.13 kilometers per second. And it's pretty big in the sky. It's 28 arc minutes across. That's as big as the moon. So that's pretty big. I thought M20 was a glob, though. Going to have to dive into this a little bit more. I have to dive into this a little bit more because I remember M20 being a globular cluster, not an open cluster. But hey, what do I know? So these are all the different names for M20. All the different names. They even include the Trifid Nebula, which I have a problem with that. Trifid Nebula. Yeah, okay. Yeah, yeah, I can understand that. M20, the I I guess what they're saying is that the cluster is associated with um, the nebulosity, and so okay, so they're calling M20 a cluster, and the Trifid Nebula um, something else. I don't know. Got a problem with that one. Anyway, here's all the other names for this object. Quite a few different names. Does it have an NGC number? It does have an NGC number as well. Most objects, most astronomical objects at least, have many, many names. So quite a few references to this object. References are just papers, professional journal papers that have in some way mentioned this object. Now, I've investigated this a little bit, and I haven't really found a lot of consistency with that. Um, so yeah, I think something needs to be done about that because if Simbad says that this object is supposed to be in this paper, is mentioned in this paper because that's how we measured its distance. And I did this the other night, right? In fact, let's try to do it here, right? There's one distance measurement to this object. So let's take a look at it. Where is it? Okay, so this says that it's 816 parsecs away. 1 parsec is about 3.26 light years. So 3.26 times 816 is 2,660 light years away. Now, supposedly, this paper, this is just a reference to a paper that was published back in 2005. Supposedly, this paper is going to mention how they measured that or in some way got that number, right? This is the only reference I see. So let's click on that, and that will take us to the ADS, which is the Astrophysics Data System. If you want to find any paper, any kind of astronomical paper, go here for sure. Hit archive.org first, but if you can't find it there, go here and you'll probably find it. So there's the publisher's PDF. So again, it's the same kind of thing. It's just freely available, which is awesome. Thank you for all of that. It doesn't really cost the publisher all that much though. So astrophysical parameters of galactic open clusters, okay? Published in January of 2005. So let's find out if M20 is mentioned, okay? We can do a search, right, for M20. No, M20 is not found. Go M space 20. Not seeing anything. Nope. Nothing there. Let's see. Let's go back to the NGC number, see if it's listed as an NGC number. Isn't this frustrating? I don't know what's going on with this. So NGC 6514, that's the same object. So let's go 6514, 6514. No, nothing. But apparently, according to the abstract, they present a catalog of astrophysical data for 520 galactic open clusters. So maybe this list is not, yeah, see, the catalog of open cluster data and the open cluster diagrams atlas are only available in electronic form. So they're not published in this paper. Frustrating. Okay. Well, that's a useful piece of information, at least. So I'll have to find another way to get these lists. But apparently these guys did. And it's in a catalog that is not in this paper. So that's understandable. You know, I don't know if you knew this or not, but most journals, in fact, all scientific journals, as far as I know, they charge the authors to publish. And depending on what journal it is, it can run up to $500, maybe $1,000 a page per page. So it's understandable that, you know, if you have, you know, 100, 200 pages of just, you know, catalog information, you're not going to be able to afford the publication costs on that, right? I mean, it runs huge. So yeah, that's understandable. That's totally understandable. So yeah. Anyway, let's keep looking at M20 here. Let's see what else we can find. So pretty active in terms of references, right? There was a total of 361 references. And again, you know, these are papers that supposedly has mentioned this object, and we can display those. I'm not going to go through all of them, of course. That would take too long. But you can see these are all papers. Most of these, I would say, are freely available. And as you can see, they are timely, right? That says 2017. So, you know, within the past year, some interesting work has been done on either, you know, specifically this object, M20, or objects like it. That's pretty cool. They're looking at it with ALMA, uh, collisions, observational signatures of cloud collision. So yeah, you know, M20 is a very cloudy region. So I'm not surprised that they are looking at it, you know, with radio scopes, submillimeter scopes like ALMA, looking at star formation regions, OB stars, really large, big blue bright stars, newly hatched, star cluster formation theory. Awesome stuff. If you want to dive into any of these things, it's absolutely fantastic. Susan O'Hare is in the house, and she was watching a terrible movie. And you'd much rather watch this. All right. I like you. We're just looking at all the references to a Messier object called M20, which is a cluster of stars and a big cloud of gas and dust. I thought it was a globular, but it most definitely is not. So yeah, that just goes on and on and on. Isn't that great? Lots and lots of papers that supposedly mention M20. I'm going to go down to the bottom here and see what else we have. Observing logs. So we established that it was how far away? How many light years was that? Like 2,600. So that's pretty close, right? Our galaxy is about 100,000 light years across. So, 2,600 light years, that's pretty small. That's not very far. That's still in the neighborhood. What else we got here? I don't know what this is. Oh, did we get a brightness of that thing? A magnitude? A visual magnitude? Let's find out. Oh, I don't see any. I don't see any visual magnitudes on that. Let's go over to the pictures. Everybody likes pictures. And it's probably going to be all zoomed in. So let's back up a little bit. These are images probably from the Digital Sky Survey. That's sort of the default uh, catalog that comes up here. It's a beautiful region, of course. This nebula here is called the Trifid Nebula, and it's called the Trifid Nebula because it's sort of divided into. It's got these three. It's hard to see here because it's overexposed, but it's sort of got these three dark bands in it, so it sort of divides it up into three. Hence the name Trifid. It's a real stretch, but this is looking towards the center of the galaxy. So there's a lot of stars. There's a lot of gas and dust. The stars inside of here, which are M20, um, are is making all this gas and dust glow like that. So that's why it's so bright. It's because there are stars inside of here that are making it all glow. Let me zoom out one more time. And really get a good idea of what's going on. This big blob down here is called M8. It's also known as the Lagoon Nebula, and it too is just a gaseous um, um, nebula. There's a bunch of stars inside. It's a cluster of stars as well that is making all this stuff glow. But great structures, great structures. You can really, when you've got gas and dust around, you can really get a good idea about, what kind of things are going on in these regions. There's a lot of action going on out there. So, so this object, I think, as we calculated, was like 2,600 light years away. So in this case, some of the stars that you're seeing here are going to be in the foreground, and some of the stars are going to be in the background. I would say, just as a general guess, that most of the brighter stars here that you're seeing are probably in the foreground. They're probably between us and it. And probably the fainter stars and even this gas and dust stuff here is probably behind it. So that hopefully gives you a little sense of depth. Yeah, we've got two Susans. I've I've doubled the number of Susans in here. That is progress. That is definitely progress. That is very awesome. So let's scan around a little bit just for fun. I don't know why it keeps jumping around like that. This is a very interesting region of the sky because there's a lot of stuff. There's a lot of dark stuff, and there's a lot of stars. This is kind of a neat region here. Do you see? It's it looks like there aren't a lot of stars here, right? Well, that's not because there's a gap in the stars. Okay, uh, stars are pretty uniformly dispersed. But what's happening here is that we've got this dark cloud between us and the background stars, and so it's blocking out a lot of the background stars. So you're only seeing stars that are in front of this dark cloud. And the reason why it's a dark cloud is that there aren't any glowing stars inside of it to make it glow, like you can see here. Isn't this kind of neat? I just, I'm looking at these things and noticing like little bubbles, right? Little round bubbles. Here's 1, 2, 3, maybe. I don't know. Kind of neat. Kind of neat. But yeah, so this is not a lack of stars in these areas. What it is just dark gas and dust that's blocking all the background stars. And so it looks like it's a hole, right? Just not a lot of stars there. But rest assured, it all looks like that. Okay, this is sort of a uniformly dispersed stars. There's, dark clouds in there too, but if these dark clouds weren't here, it would look a lot like this. Now, I'm not quite sure why there's two different colors here. See how this is sort of bluish or grayish, and this is sort of orange or red? I'm not quite sure why that would be happening. That might have to do with some larger scale dust things. Yeah, it's hard to know. Hard to know. It almost is like they're, combining data, from different um, telescopes and trying to do their best to match up colors and not doing all that great of a job. Anyway, these two objects for sure are great to see in binoculars, definitely a telescope. Very, very awesome. But today's object was M20, which is an open cluster inside of this nebula that is called the Trifid Nebula. So I'll zoom back in on that, and I'm noticing that I'm over my hour already. It's really unbelievable how fast this hour goes. I hope it's almost as fast for you. I hope this isn't too boring. I don't think it is. But I think with that, I am going to come back over here, and I'm going to stop sharing, and I'm going to pop back in and take one more sip of this wonderful, wonderful chemical. Cheers. And I think I'm going to exit for the day. Now, as I said at the beginning of the show, I made an error yesterday, right at the end. I said that in one day we'll have moved about 1 million kilometers. No. 20 million kilometers. So in one day, just just sitting right here, not doing a thing, right? Not doing a thing at all. Um, in one day, we spin around the Earth once, and then we move around the sun a little bit, and then our entire solar system moves around the galaxy just a little bit. And if you add up just those three motions, we move 20 million kilometers a day. So, we're moving really, really well. And we are space travelers. We don't really think of it that way, but we are space travelers. We are moving through space. We are hurtling through space. We're actually doing sort of a spiral pattern through space as well. So yeah, it's a dizzying thing, but I think I'm going to take off for today. I've got to get back up to the ship. They are yeah, they're calling. They're calling. So I've got to get back up. Yeah. So I will see you 20 million miles out that way. I think it's that way. Um, in a little less than 23 hours from now. So, yeah, I'm going to get out. So, take care, everybody. Have a great day. Have a great evening. And I will see you tomorrow. Take care, everybody. Bye. Peace.